Hello everyone. Let's start solving the JAM question of 2022, the organic questions, right? So let's start. The first question says the reagent required for the following transformation is. So what you see is you have a molecule on which you have ketonic group and you have carboxylic acid group. What is happening is carboxylic acid is not touched, whereas your ketonic group is getting reduced. So and it is getting reduced to CH2. So if you want to reduce C double bond O to CH2, there are two named reactions with which you can do it very efficiently. One of them is Clemmensen reduction and second one is Wolff-Kishner reduction. In Clemmensen reduction you use acidic condition, that is zinc amalgam and HCl, and when you use Wolff-Kishner reduction you have to use basic condition, that is hydrazine and KOH. So of course here the answer is zinc amalgam and HCl. So this will be your product, right? Shall we look at other options also? Let's look at it. Okay. Right. First one is NaBH4. NaBH4 is very mild reducing agent. It will not touch carboxylic acid, but it will reduce ketonic group into alcohol. Okay. LiLH4, very powerful reducing agent, will reduce both ketone into OH, alcohol, and COH also into alcohol, that is CH2OH. BH3 is electrophilic reducing agent. It accepts electron and does. So it will not touch the ketonic group, but it will reduce the carboxylic acid to CH2OH. So the answer remains is zinc amalgam and HCl. Okay. Let's move ahead. The second question. The major product formed in the following reaction. So what you are doing is hydroboration oxidation reaction. So in hydroboration oxidation reaction you convert alkene into alcohol. So you add basically hydrogen from BH3. Generally we use BH3, here they have used BD3. So hydrogen has been replaced with deuterium. So you use BH3. So what happens is you add water. In this overall reaction you add water across double bond. So water has H plus and OH minus. Okay, water has H plus and OH minus. So it adds water across the alkene by anti-Markovnikov's rule. So what is Markovnikov's rule? Markovnikov's rule says negative part goes to carbon having less hydrogen. Here negative part will go to carbon having more hydrogen. So negative part is OH minus, positive part is this. So on this carbon if you see there is 0 hydrogen, whereas if you see on this carbon you have to look only at the alkene. If you look at this, this has 1 hydrogen. So what will happen? So negative part will go to carbon having more hydrogen because we are following anti-Markovnikov's rule. So here OH will get added, OH will get added, and here H will get added. Okay, here H will get added. That's what is hydroboration oxidation reaction. And apart from that, what happens is the addition of H and OH is by syn fashion, the mechanism which we will do very soon. So both of them will attack from the same side. So with that rule, let us look into it what happens here in this question. So let's start attack with the BD3. So BD3, the mechanism is concerted, both of them attack simultaneously. But thing is, boron, boron has 3 bonds. So its octet is not complete, only 6 electrons there. It's electrophilic in nature, it accepts electron. So first pi bond attacks. Important part is first pi attacks from this side. Why? So that once it attacks from this side, you are getting carbocationic character here on this carbon. If you get carbocation on this carbon, this is tertiary carbocation. Had it attacked boron from this side, then you would have got positive charge on this carbon. This carbon would have been secondary carbocation. And we all very clearly know that tertiary carbocation is much more stable than secondary carbocation, and therefore it attacks from this side and deuterium attacks from this side. Now you can see I have made solid lines. What I am trying to say is this attacks from top. So deuterium also goes and attacks from top. It could have been from bottom, like this could have attacked from behind the board, behind the screen from where you are watching. Then it would have been same fashion of addition. So D2B would have attacked from behind, and this deuterium also would have attacked from behind. and therefore you get racemic mixture in the product. As you can see, in all the options they have given plus minus both, so racemic mixture. Okay, so let us go if attacks from top, so you get BD2 and D here. So this mechanism involves like 2 times again alkene will attack on this thing. So this alkene will go and attack boron, deuterium will come here, so you will get same product. So thrice you will get, so trialkyl borane you get. Then next what happens? Next H2O2 will attack. So next when H2O2 attacks, so H2O2 first reacts with OH minus to give OOH minus, and then this O minus goes and attacks on this boron, and sorry, by mistake this H has come, I will change that. So this O minus goes and attacks on boron, and boron gets negative charge. Okay, and then what happens is, then this alkyl group moves on this oxygen, this moves out, and then you get alkoxide on the boron. So 3 times this will happen and you get this one, then you hydrolysis, you get this one. So what has effectively happened is, understand this part, let's look into it once again. This boron is attacking on this carbon, deuterium is attacking, and then the OH minus which is attacking is not from behind, there is no inversion of configuration, the configuration remains. So the OH will come towards the viewer and deuterium also towards the viewer. So your answer will be B. Okay, your answer will be B. That's it. Next question. This is a very simple question. So here you are having a molecule where the benzene has 2 CHOs. Okay, they have 2 CHOs next to each other, and you are using concentrated sodium hydroxide and you are refluxing it. So here the important thing is it cannot undergo aldol reaction, because for aldol reaction you need carbon next to CHO which should have hydrogen, that means alpha hydrogen containing carbon, that is not there. So only thing what you can think about aldehyde reaction with NaOH is apart from aldol reaction is Cannizzaro reaction. So this is simple Cannizzaro reaction. In Cannizzaro reaction generally two different molecules are involved. One of them gets oxidized to COH, another gets reduced to alcohol. So here, but in the same molecule CHO is present, so one of them will get oxidized to acid, another will get reduced to alcohol. So let us see the mechanism. It is little bit different mechanism because hydride shift takes place, from carbon hydrogen bond is breaking. That's not it's not very commonly seen. Okay, so this OH minus goes and attacks on this carbon, this goes up, then it comes down. This H minus comes and attacks here, you get O minus, and this picks up proton and you get CO minus CH2OH. If you do acid workup, you will get COH. Okay, so this is the answer. So answer should be option number A. See, this one of the CHO gets reduced to CH2OH, other CHO gets oxidized to COH, right? Next question. Which one of the following option best suited for affecting the transformation? Okay, so you are having aldehyde and you are having secondary alcohol. In the reaction, alcohol remains untouched, whereas aldehyde gets oxidized to carboxylic acid. So what are the reagents? First is MnO2. MnO2, what it does is basically only it oxidizes alcohols, that too not alcohols, all alcohols, only benzylic and allylic alcohol, something like this. Okay, if you are having something like this, so if on benzene next to it is CH2 and then you are having anything X, then it will call benzyl halide. If you are having OH, then it is called benzyl alcohol. So you need something like this. Only when this is there, if you oxidize, becomes aldehyde, or you are having something like this, allylic. Okay, so if you are using MnO2, it will oxidize. But if it is normal alcohol, it won't touch also. You can see here I have written here, it won't even touch, no reaction will happen. Next reaction is what is called a Swan oxidation. Swan oxidation, you use DMSO, oxalyl chloride and triethylamine, and you carry out reaction minus 78 degrees Celsius. Though they have not given, it's understood. Okay, so once you do this, Swan oxidation is very specific. It will never oxidize alcohol more than carbonyl. So if it is primary alcohol, it will stop at aldehyde. Aldehyde will not get oxidized to acid. If it is secondary alcohol, anyway it cannot get oxidized to acid, so it gets oxidized to ketonic group. It does not touch aldehyde. Very important. Swan oxidation is for selectivity. It will not touch aldehyde at all. It will oxidize alcohol to aldehyde and stop there. Next is interesting. So this is open R oxidation. So open R oxidation is opposite of MPV reduction. So here you use aluminum isopropoxide and generally we use along with it acetone. So that will oxidize secondary alcohol into ketone. Very important. Secondary alcohol into ketone, and acetone gets reduced to alcohol. Okay. Last is the right answer because you are using Ag2O and ammonium hydroxide. So generally we use silver ammonium, ammonical silver chloride, but this also is pretty much same tolerance reagent. It specifically it is used if you know this reaction. If you have if a given compound is there, unknown compound is there, you put 2,4-DNP, it gives you yellow precipitate, so you know it is carbonyl. After that, if you want to know it is aldehyde or ketone, then you do silver mirror test, because aldehyde CHO will get oxidized to COOH, whereas ketone will not get, and it does not touch alcohol at all. So that's what it happens. Here you are having Ag plus, so Ag plus itself gets reduced, Ag plus itself gets reduced to Ag0, that is metal silver, and that's what you see on the side of test tube, silver mirror. And what happens in the process, CHO, the aldehyde gets oxidized to carboxylic acid, you get COOH. Okay, so this one gets COOH and Ag plus gets reduced to Ag. So this is the silver mirror test, and therefore the answer is option number D. Okay, now the last question. Among the following molecule, the biomolecule which has direct metal carbon bond is. So direct metal carbon bond, this coenzyme B12 actually has, I looked into it, I was also not very sure. So it has cobalt carbon bond, and that's what is responsible for the reactivity. Nitrogen is quite complicated protein structure. Chlorophyll and hemoglobin, they both have porphyrin structures, and 4 pyrrole rings forms this porphyrin ring, and all the pyrrole rings nitrogen are involved in bonding with. Chlorophyll has manganese and hemoglobin has iron, and that's how it forms the reaction. So the answer is option A. So we'll do the next 5 questions later.